Good morning. So this is 36th session, and in the previous lecture we discussed about the laminar and turbulent flows through ducts. Today we will start our discussion for viscous flow in non-circular ducts. Whenever we will be doing various engineering and industrial applications, we will be finding that it is not only the circular cross section which is used in industry, but there can be some other cross sections. Okay, so typically I have shown you different cross sections. For example, this is a rectangular cross section, first one, then second one is a square cross section, third one is a triangular cross section, fourth one is an elliptic cross section. So these are some of the commonly used cross sectional shapes, and other than that also we can have other geometrical shapes. Okay, so whenever the cross section of the duct changes, then what are its implications on pressure drop characteristics or friction factor characteristics? That is what we will try to establish over here for both laminar as well as the turbulent flows. Okay, so what I have done is actually I considered a duct which is nothing but a non-circular duct. Okay, and this duct can be of any cross section. Over here at the moment I am not specifying any specific cross section of the duct, but I am considering a generic geometry. Okay, so if I have an inclined duct, so say L is the length of the duct, and it is inclined at an angle phi. My gravity field is acting in the vertical direction. Tau W is the wall shear stress at the wall of the duct. So of course, when you will be considering the non-circular ducts, for some of the cross sections you may find that across the entire edge of that particular cross section shear stress may not be same. Okay, so that's why whenever I will be defining this tau W, I will consider tau W bar over here. So basically I am trying to consider over here the average wall shear stress. Is this point clear? So now this is the tau W as the average wall shear stress, and if say some pressure Pi is at this point inlet, and say PO is the pressure at outlets, then of course Pi has to be greater than PO. So I will be having net force because of pressure in this direction, delta P. Okay, so now if I write this force balance based on the equation of momentum, so what I will be getting, sum of all forces is equal to rate of change of momentum. Okay, so if I consider that my cross section of the duct is not changing along the length, then of course velocity at inlet as well as velocity at outlet will be same, and rate of change of momentum will be equal to 0. This part also we have done earlier. So now I am writing on the left hand side all the forces which are acting on this fluid element, these to be equal to rate of change of momentum, which is nothing but equal to 0. Okay, so now you can see that delta P, so whenever I was considering the circular cross section, this cross sectional area on which delta P is acting, I wrote pi r square. Now here, because I have not yet defined that what type of cross section I am having, I am considering a generic case, that's why I am writing this area as A. So A is nothing but my cross section area. So this is cross section area. Point is clear. Then tau W is the average wall shear stress, and this tau W will be acting on the periphery of the cross section. So if I have any type of cross section, then of course I can define the perimeter of that cross section. So perimeter will be nothing but this sum of all these sides. Okay, so that is my wetted length, and if I multiply that perimeter with length, then I will be getting nothing but the total surface area on which this wall shear stress is actually acting. Is this point clear? So that's why tau W I have written as perimeter times L. And if you talk about a circular cross section, for circular cross section perimeter is nothing but equal to 2 pi r. So that's why for circular cross section we were directly writing 2 pi rl, but for a generic cross section we will be writing perimeter into length. Okay, that will be the surface area of the duct on which my wall shear stress is acting. Then I have this third component which is coming because of the body force. So body force will be, gravity is in downward direction, so along the length of the duct you will be finding that G sin phi is component of the gravity. So sorry, this will be plus, so this is positive in this side. Okay, so plus rho G L sin phi equal to 0, and of course this L sin phi will be representing nothing but change of elevation between point 1 and point 2. Okay, so now after dividing by rho g and a the complete equation and then bringing tau w to the other side, I can say that delta p by rho g plus delta z, which we call as nothing but the head loss, that will be equal to tau bar w into perimeter into length divided by. Okay, is this point clear? So now from here I can also rewrite this equation as hf equal to tau bar w into L divided by A by perimeter. Okay, so now if you recall the relation from the circular cross section, so for circular cross section my head loss was nothing but equal to tau w L divided by radius of the duct. Okay, so it means that this particular parameter, which is cross sectional area divided by perimeter, this has to be equal to something identical to radius. So we call this as RH, where RH is nothing but hydraulic radius of the duct. Is this one clear? Okay, because for circular cross section my HF was equal to tau W into L by R. So for non-circular cross section I am getting HF is equal to tau bar W L by A by rho. So A by rho must have the dimensions or equivalence. If I consider its equivalence to that of a circular duct, so it must be identical to something called as radius of the duct. Okay, so for a non-circular duct we cannot define exactly the radius. That's why this equivalence of cross-sectional area by perimeter is something which is called as hydraulic radius of the duct. Is this one clear? So it means for non-circular duct I can simply write head loss as average wall shear stress times length divided by RH, where RH is nothing but cross-sectional area by perimeter of the duct. Is this one clear? And if you consider this to be your generic formula, now if you substitute over here the area and perimeter for a circular duct, you will be finding for a circular duct area is pi r square and perimeter is 2 pi r. Okay, so area is pi r square and perimeter is 2 pi r. So you will be finding that pi r cancelling and it is becoming identical to r. Fine. Now what else we can do? We also know that one correlation, particularly from the study of circular ducts, that F is equal to, this relation also we have derived in circular ducts, that F is equal to nothing but 8 times tau W by rho V square. Okay, so this is something while we discussed the circular ducts, at that time we have derived this, that friction factor is equal to 8 times tau W by rho V square. Okay, so this is something which we have done earlier. So for non-circular ducts, my tau W can be written as HF into RH by L. Is this point clear? Or in more generic sense, let me write. Now what I will do, I will substitute this value of tau W from here into this particular equation. So if I do so, what I will be getting? 8 times, in place of tau W, I can write HF into A by perimeter. Okay, HF into A by perimeter divided by L. Okay, divided by L and into rho V square. Is this one clear? So from here if you see, your HF will become F into L into rho V square. Fine. FL rho V square divided by 8 into A by perimeter. Is this one clear? That is something I am getting from here. Yes. So what I told you that F is nothing but equal to 8 tau r W by rho V square. Okay, so this has become equal to 8 times HF into A by rho by L rho V square. Okay, so from here if you calculate HF, that is coming out to be FL rho V square by 8 A by rho. Okay. So now what I can do, I can write this FL rho V square by, in place of 8 I can write it 2 times, because I want to make analogy to that of a circular duct. So if I have to make analogy to that of circular duct, I can write it 2 into 4A by P. Okay, is this point clear? Somewhere I think I must have one rho g term in the denominator. Is this dimensionally correct? Yes, wall shear stress is having dimension of pressure, and this is also pressure. So where we have done mistake, let me just see. Oh yes, understood. So when I have actually divided this by rho g, I must have one rho g in the denominator. Please make this correction. Okay, so while I have calculated this, I have done division by area as well as by rho g. So I forgot to do this rho g division on right hand side. Okay, so if I do this rho g division on right hand side, then ultimately in place of tau r w, I will be getting 1 rho g in multiplication also. Is this one clear? So this rho g will come in multiplication. So once it is in multiplication, then it will come in the denominator. So now rho will get cancelled. This rho can be cancelled with this. So ultimately I will not be having rho over here, but I will be having FL V square by 2 into 4A by rho, and I will be having G also. Okay, is this point clear? What is A by rho? A by rho is already we have defined as hydraulic radius. Okay, so FL V square by 2G into 4 times RH. Okay, so what about corresponding case for a circular duct? For a circular duct, we define HF is nothing but equal to FL V square by 2GD. Okay, so if I make analogy with the case of a circular duct, I will be finding that 4 into RH is actually our dimension, which is coming identical to the case of a equivalent diameter for a circular duct. Is this point clear? So if I make the analogy of a non-circular duct with a circular duct, for which our Viscous equation is FL V square by 2GD, so I will be getting, by comparing this, that this 4 into RH is something which is identical to diameter of a circular duct. Okay, so I can call this 4 into RH as nothing but DH, which is called as hydraulic diameter. Though my duct is non-circular, but hydrodynamically the equivalent diameter of that particular duct, which makes its analogy identical to that of a circular duct, is called as hydraulic diameter. Is this point clear? So from here I have got one important correlation, that head loss for non-circular ducts will be nothing but equal to FL V square upon 2G DH, where DH is my hydraulic diameter and it is nothing but equal to 4 into cross-sectional area of the duct, because RH is A by perimeter of the non-circular. Okay. Up to this point, is it clear? So this is the generic idea. It means that whatever till now I have studied for the circular duct, same analogy I can apply even for non-circular ducts. The only correction I have to do is, in place of diameter, I have to use the hydraulic diameter of the duct. Okay, is this point clear? So now we have made this basic analogy based on the geometry and the force balance along the streamwise direction. Now what we need to do, we need to check this hypothesis by testing for different non-circular geometries whether this hypothesis is correct or not. Okay, so whatever geometrically we are finding that if we simply substitute the diameter with hydraulic diameter for non-circular ducts, then whether I am able to correctly calculate the pressure drop or head loss, that is something which we want to ensure now. Okay, so for doing that, let us first consider that we want to establish head loss relation theoretically for laminar flow through long plates. Okay, so I have one plate like this, other plate like this, and these two are say separated by distance 2h. And of course these plates will be having width, so say B is the width in the third direction and B is something which is approaching to infinity, so means B is very large. Fine. Now if top plate is also fixed and bottom plate is also fixed and flow is happening in this direction and say L is the length. Okay, so if I have to measure, I have to fix the coordinate system, say this is my y coordinate, this is my x coordinate. Fine. All are clear with this idea? So now, can you tell me, if I consider the fully developed laminar flow over here, what will be formulation of velocity profile for this type of situation? We have already done this case while we saw the applications of NS equations. Is it something like this? What was the mathematical equation? Say at this point I have u max. What was the mathematical equation? Not ux, uy. Uy equal to u max times y square by h square. Okay, so that was the, because this distance from here to here is h. Fine. So this was the relation which we derived actually earlier. So now, if flow is fully developed, then of course at each and every point of the length of this plate, everywhere I will be having same value of the wall shear stress because velocity profile is not changing. So say this is my wall shear stress tau w over here. So if I need to calculate tau w, how I can calculate? Tau w will be mu times mod of du by dy at y equal to h. Fine. So from here what I will be getting? Mu times u max into, it will be mod, so 2h by h square. So ultimately my wall shear stress is coming out to be 2 mu u max by h. Okay, is this one clear? One more important relation we made, that u average, let me write it to equal to v. Okay, because v is the velocity which we are using in streamwise direction, v as the symbol for average velocity. So u average, which is nothing but equal to v, that has to be equal to, for this type of flow, this is nothing but a plane Poiseuille flow. So for plane Poiseuille flow, we derived earlier that average velocity is equal to 2 by 3 times of maximum velocity. This relation we derived earlier for plane Poiseuille flow. Okay. So here our average velocity, which is v, that has to be equal to 2 by 3 times of u max. So it means u max I can replace with 3 by 2 times of v average. Okay. So tau w will become, from here 2 will cancel, 3 mu v by h. Is this one clear? So now if I substitute this back into my head loss equation, So what is head loss equation? You see the more generic form. Yeah, when I have applied the momentum equation in streamwise direction, then my head loss is equal to tau w into uh, perimeter into length divided by rho a g. Okay, so tau w into perimeter into length divided by rho a g. Okay, and tau w I have got equal to 3 mu v upon h, and this has become into L and rho g times area by perimeter. What is area by perimeter for this type of situation? Now we need to calculate area by perimeter. What will be its area? Two H into B. Okay. 2B into H is the cross sectional area. Okay. And what will be perimeter? B plus B means 2B plus 2H. 2H is one side, 2H is other side. So it will be 4H. Fine. Is this one clear? So from here, of course, as I told you that B is approaching to infinity. So if I have to calculate this A by perimeter, then what I have to do? I have to over here introduce the limit B approaches to infinity 2BH divided by 2B plus 4H, and what you will be getting out of this? If you divide throughout by 2B, only H. Is it correct? Only H? Okay, so A by P is coming out to be H. Okay, so from here, what I will be getting, that HF is equal to 3 mu LV upon rho G into A by P is also equal to H, so rho G into H square. Okay, so it means theoretically for fully developed laminar flow, like what we are getting, head loss is equal to 3 mu LV by rho G H square. Okay, whereas for circular duct it was equal to 32 mu LV by rho G D square. Is this one clear? For a circular duct for fully developed laminar flow, it was equal to 32 mu LV by rho G D square, and for non-circular duct, particularly having the rectangular cross section, I can say that it is equal to 3 mu LV by rho G into H square. Okay. Now, not exactly, yes, rectangular cross section, but with one dimension approaches to infinity. Because if I consider that that particular dimension to be finite, then some other wall effect will also come into picture, and velocity profile will not be the exactly same. Okay, so now what I need to do, if I want to make the analogy in order to find out friction factor for this situation. Okay, so what will be friction factor for this situation? HF is equal to 3 mu LV by rho G H square. I can, if I have to calculate the friction factor, then I can equate it to generic pressure drop equation, which is equal to FL V square upon 2GD, and this is a non-circular duct, so in place of D I have to write over here DH. Is this point clear? So now this left hand side H square also I want to make it identical to hydraulic diameter. Okay, so what is the hydraulic diameter of this? Hydraulic diameter will be 4A by P. So if A by P is H, then of course 4A by P will be equal to 4H. Okay, so from here what I will be getting that HF is equal to 3 mu LV upon rho G. Now I want this H to be equal to hydraulic diameter. So what I will be doing, one hydraulic diameter is equal to 4H. I have H square, so 4H into 4H will become 16 H square. If I am dividing here by 16, I must multiply in the numerator by 60. Okay, so that will be equal to FL V square upon 2G dH. So now this 16H square term has become identical to dH square. Is this one clear? Now what I need to do, at this 16 into 3, it will become 48 mu. This length is cancelling out, one velocity is cancelling out there, G is cancelling, 48 mu into 2 I will be getting over here. This dH has cancelled with this. So 48 mu into 2 divided by rho V into dH equal to F. Okay. So from here what I will be getting, that F is equal to nothing but 96 by Reynolds number if it is calculated based on hydraulic diameter. Is this one clear? So what is the exact value? The exact value is that friction factor for this type of Poiseuille flow situation is nothing but, plain Poiseuille flow situation is 96 by RE when it is calculated based on hydraulic diameter. For a circular duct, what was this? 64 by RE. It was for circular duct, and to be precise 64 by RE dH I can write based on hydraulic diameter. So it means that under the laminar flow conditions, if I just do the replacement of hydraulic diameter into the circular duct formulation, it will be giving me some value of friction factor, but that will not be exactly correct. Okay, because if I simply replace the diameter with hydraulic diameter and just use the correlation of circular duct, the relation of circular duct which we have theoretically derived, then it is showing me significant error. Why significant error is coming into this scenario? Because the velocity profile nature will be significantly different. Okay, so that's why there is this common understanding. If I use the friction factor equal to 64 by RE based on hydraulic diameter for non-circular ducts under the laminar flow conditions, I will be getting error within the range of plus minus 40%. Okay, because if you see, this coefficient is 96, this coefficient is 64. So if you do 64 by 96, then you will be finding this error is roughly close to 33%. Okay, so error is roughly close to 33%. Okay, so that's why we need to do 96 minus 64 difference. Then it will be roughly close to 33%. Okay. No, it will be like, see, 32 by, no, not 32 by 64, 32 by 96. Difference divided by actual value. So actual is 96. Okay. So this error will be close to 33%. So it means it is bounded within the range of plus minus 40%. On contrary, if you use the friction factor as a function of Reynolds number based on hydraulic diameter and epsilon by dH, then you will be getting error in the range of plus minus 15%. So the meaning is that this is for laminar flow and this is for turbulent flow. Is this one clear? So it means that if I simply use the Moody's diagram for non-circular ducts, okay, and if I replace only the diameter with hydraulic diameter, I will be getting some value of friction factor, but under laminar flow conditions, that value of friction factor, whatever I will be getting, that will be having error band of something about plus minus 40%. But for turbulent flow, this error is very small and it is plus minus 15%. The reason is that in case of laminar flow, there will be significant changes in the velocity profile. On contrary, the theory of turbulent flow is derived based on the logarithmic velocity profile, which is remaining identical for almost all types of ducts. So that's why error encountered in case of turbulent flow by just using the analysis of circular profile is actually very less. Is this one clear? So for this plane Poiseuille condition, because theoretically we have seen the theory of laminar flow, which gives us friction factor is equal to 96 by Reynolds number. Let's also try to see the corresponding theoretical relation for friction factor if I consider the turbulent flow profile. Okay. So for turbulent flow, once again we will be using the logarithmic velocity profile. Okay. So what is the logarithmic profile? Now one thing I am writing over here, capital Y. Why I am writing capital Y? Let me tell you. So this is the situation. This is center line. This was my small y and this was small x. Okay. So whenever we write this logarithmic velocity profile, we have to measure the y parameter from the wall. So if small y is from the center, then I can say capital Y is my dimension from the wall. So if I consider this point, for this particular point my velocity will become u capital Y by u star, and for turbulent flow we will be considering nothing but the logarithmic velocity profile. So 1 by kappa into ln of y u star by nu plus b, and this is applicable for value of y from 0 to h, because at this point y is 0 and at the center y is h. From other side also I will be having the simple. Is this point clear? So this is capital Y equal to 0 and capital Y equal to h. Fine. Now in order to find out the average velocity, what I need to do? I need to consider 1 by area times integral of u dA. Okay. So width I have considered unit over here. So 1 by h integral 0 to h u dy, and this will be my nothing but velocity profile. Once I have the velocity profile, I can calculate the equivalent wall shear stress and then I can obtain the value of friction factor. Okay. So after calculating the wall shear stress, I will be getting value of friction factor as 1 by f power 1 by 2 nearly equal to 2.0 into log of Reynolds number calculated based on hydraulic diameter power f1 by 2 minus 1.19. So you can see that this equation is similar to the one which is obtained for circular ducts. Fine. So this equation is almost exactly the same. There is slight changes in the coefficients. Otherwise, the whole form of equation is coming same, whatever we have seen in case of circular ducts. Point is clear? But it was observed that if we slightly modify this equation by just changing this coefficient to 0.8 and inside the log term, if I multiply 0.64. Is this point clear? Though theoretically I am getting one equation which is almost identical to that of a circular duct. Okay. But if I slightly modify this equation by multiplying here 0.64 and changing this coefficient to 0.8, then my experimental data is actually matching quite well. Okay. So what I can do, I can simply say that this 0.64 is some coefficient which is acting as a correction to my hydraulic diameter. Fine, because in this Reynolds number, one hydraulic diameter is in the multiplication. So basically this 0.64 is nothing but acting as some sort of correction to hydraulic diameter, and it is fitting my data well. Now this 0.64 is also having some connection to the laminar flow analogy. In case of laminar flow, we found that my circular equation was 64 by Re dH, and non-circular equation has come for this situation 96 by Re dH. So it means this coefficient was only creating the difficulty. Okay, so it means that if I consider the ratio of these coefficients, so 64 by 96, which is coming equal to 2 by 3. So if the meaning is, if I consider the circular flow correlation only, even for laminar flow theory, and in place of hydraulic diameter, if I use my some another effective diameter term to be 2 by 3 of dH, then I can simply use the circular flow correlation. Okay, so this 2 by 3 is once again coming close to 0.67, which is almost very close to the correction factor which we are getting for the turbulent flow. Is this point clear? So from here, one conclusion we can make, because the analysis of laminar flow theory is easy, so one simple conclusion we can make, that we will be only doing the laminar flow analysis for non-circular ducts, and whatever the difference of coefficient is coming, with that difference of coefficient we will try to calculate the effective diameter, which is some coefficient times hydraulic diameter, and whatever that coefficient we are getting, if we simply use that coefficient as correction for hydraulic diameter in my circular duct turbulent correlation, then same correlation can be applied for non-circular ducts also. Point is clear what I have said? Okay. So only thing, if now you have any other non-circular geometry, what you need to do simply, you need to only calculate the laminar flow theory. From laminar flow theory, you then correlate the coefficients for circular and non-circular ducts, and whatever the correction of hydraulic diameter is coming to make the effective diameter, that particular coefficient you multiply in hydraulic diameter for turbulent flow also, and whatever the turbulent flow correlation of turbulent flow relation of circular duct is there, same can be used with very good accuracy. Okay, so that's why I have generalized this. So if we use our D effective to be only equal to hydraulic diameter, then we will be getting some reasonable accuracy. But if we want extreme accuracy, particularly from the research perspective point of view, then we can use effective diameter, and this effective diameter we can simply obtain from the length. Is this point clear? All are clear with this generalization? Now this generalization we can use for all other non-circular geometries. Okay. So other non-circular geometry is flow through concentric annulus. So here what I have in the center a solid tube. So this is a solid tube at the center, and this outside is one another tube, and this space is actually hollow space where my flow is happening. So flow is happening in the annular portion between the two tubes. Okay, you can see that if I draw the velocity profile over here, so velocity profile will be something like this, because this inner wall is also stationary, outer wall is also stationary. So considering that, something like this will be my velocity profile. Okay, and I have fixed my coordinate system at this point. So this is my radial direction, so, and this is my axial direction x. In the radial, in terms of radial direction, I am considering that r equal to b. This is the size of the radius of the inner cylinder, and r equal to a is the inner radius of the outer cylinder, and this is outer radius of the inner cylinder. Fine, r equal to a and b. Now of course this is in the cylindrical coordinate system, so if I consider the commensurate Navier-Stokes equation in cylindrical coordinate system, then I will be getting d by dr of r mu into du by dr equal to kr, where k is nothing but d by dx of p plus rho g z. Okay, and from here, this I am not doing the complete derivation, just I am writing the main points. So if you do this integration 2 times, you will be getting this as your nothing but the velocity profile. Okay, so this is the velocity profile. Now in this velocity profile you have two coefficients C1 and C2. To determine these two coefficients you need to supply two boundary conditions. So boundary condition first is at r equal to a velocity is 0, at r equal to v velocity is 0, because at this point also it is 0, at this point also it is 0. So after substituting these two boundary conditions, you will be getting the value of velocity profile. This is my velocity profile. Okay, is this point clear? This is the velocity profile, and if you have to calculate flow rate, then flow rate will be integration from B to A, velocity times area, area will be 2 pi r into dr, elementary area of the ring. Okay, and then this is the equivalent value of the volumetric flow rate. Now you can see, while I have if you want to calculate U max, so U max, you will be finding that U max is coming at some point r dash, which is equal to a square minus b square by 2 ln of a by b. So point of maximum velocity you have calculated. Okay, so you can see that point of maximum velocity for different values of b by a is actually changing, and it is coming at the close to the center point only when our B and A are very close to each other. It means when spacing between the two cylinders is very small. If spacing between the cylinders is increasing, then it is shifting towards the inner cylinder. Is this one clear? So what I am trying to say over here is, if you have very small spacing, then your velocity profile will be almost symmetric. It means at center between these 2 points you will have the maximum velocity. But if your spacing is large, then your maximum velocity will approach more towards the inner cylinder. Okay, so that is something which we are getting from this data. When this is B by A is small, it means spacing is large, then this is coming close to the inner cylinder, and it is coming at the center when this spacing is small. Okay, now we know that F is equal to HF into dH by L 2G by V square, and V is flow rate per unit area. Okay, so from here, if you also calculate hydraulic diameter will be coming as 2 times A minus B for this situation. And if you make the analogy of friction factor, F you will be getting as 64 by Reynolds number in terms of hydraulic diameter, but you will be having some additional coefficient zeta over here. Okay, so zeta is nothing but acting as the correction factor over here. So in case of plain Poiseuille flow, the correction factor was 64 by Reynolds number, 64 by 96. Here this correction factor is nothing but zeta. So that's why if I have to calculate the effective diameter will be 1 by zeta times hydraulic diameter. Okay, and if I simply calculate this effective diameter and Reynolds number, if I calculate based on effective diameter, that I can simply now substitute into the turbulent correlation of the pipe flow. Okay, and by that only I will be able to obtain the friction factor even for this concentric annulus. Is this one clear? So you can go through this point and you can try solving different numerical problems, then you will be able to see the difference. Okay. Okay, so there can be some other non-circular geometries. So okay, I will take up this in the next lecture.